All right, we are finding inverses. Inverses are super important because they allow you to find a function's identity. So let's go with some vocab. An inverse relation is when one element contains AB and the other element contains BA. So if f of x contained AB, then g of x would contain BA. If f and f inverse, and we read f to the negative 1 as the inverse, are inverses, then f of a will equal f of b if and only if f inverse of b equals f of a. Two functions, f and g, are considered inverses of each other if and only if both of their compositions are the identity function. The identity function is x, so the identity function is right here. And we know function composition is f of g of x and g of f of x. There are 4 steps to solving an inverse function. So step 1 is if the problem starts with f of x, you replace f of x with y. Step 2 is switch x and y. Step 3, solve for y. Step 4, replace y with f inverse x. All right, so let's start. It says find the inverse of f of x equals 2x minus 5. Let's start with just graphing the original. So y-intercept is negative 5. Slope is 2x, so we go up 2 over 1. And we know on this problem that we have the points, let's say 0, negative 5, 1, negative 3, and 2, negative 1. So hopefully on its inverse, we will have the points. So the inverse should have the points negative 5, 0, negative 3, 1, and negative 1, 2. So let's check and see if that's the case. So we're going to follow the steps from the previous screen. We're going to take f of x equals 2x minus 5 and replace f of x with y. Then we're going to apply step 2, which is to switch x and y. Then we're going to solve for y. And then we're going to apply step 4, which is to rename my y as f inverse x. And we have that the slope is 1/2 and the y-intercept is 5/2. So that means it goes through the point 2.5. So that's not exactly like a pretty point. So sometimes it's easier to plug in a number that we know is going to be a nice number. So if I plug in anything that, well, we could plug in our points over here and we know we should get this. So let's try that. Let's try f inverse of negative 5. And you get 1/2 times negative 5 plus 5/2. And then you get negative 5/2 plus 5/2 equals 0. So not only did we get the point here, and we can confirm that, we also have a nice starting point to now apply my slope of up 1 over 2. Inverses usually intersect, especially if they're linear. They also are what we call reflective across the y equals x line. So all inverses should reflect across the line y equals x. So it's this line right in here. And what you'll notice is, okay, this point is left 1 up 2. This point would be right 1 and then that down 2. So we're good. Okay, we can find the inverse of quadratics. So this example is a quadratic binomial. The only thing we have to do is a quadratic is not 1-to-1. So a quadratic like this, y equals x squared plus 1, would look like a graph shifted up 1. So in order for a function to have an inverse, it has to pass the horizontal line test. Well, this graph would not. It would fail many, many times. So in order to make it a graph that is having an inverse, you have to restrict your domain, and that would be at the point or the axis of symmetry where the graph starts to repeat itself. So what we're going to do is we're going to talk about our domain as x values either greater than or equal to 0 or x values less than or equal to 0. And you're going to see how the inverse also relates to that. So let's go through and find our inverse. So we're going to change f of x to y. Then you're going to switch the x and y's. You're going to solve for y. So you'll see it works. When you take something squared, you have to put a square root. But when you put a square root, you need that plus or minus. So we get y equals plus or minus the square root of x minus 1. And this plus or minus directly relates to our domain. So a square root function, graphically, would look like this. So if we want them to be symmetric about that line y equals x, when you take the positive original, you want the positive square root. When you take the negative original, you want the negative square root. So that means that if you're going to use the positive square root, your domain is x greater than or equal to 0. If you're going to use the negative square root, then your domain would be x less than or equal to 0. So one of the things we learned in our definition that we can state two functions are inverses if and only if their composition is equal to x, where we refer to x as the identity. So what we're going to do now is apply some function composition and determine if two functions are inverses. So we have f of x equals 3x minus 3 and g of x equals 1/3 x plus 5. So what we're going to do is plug in 1 to each. So let's start with f of g of x. So that means I'm plugging g into f. So we're going to have 3 1/3 x plus 5 minus 3. So distribute your 3 and you get x plus 15 minus 3. So that gives x plus 12. Does x plus 12 equal x? And no, they do not. this has plus 12, this has just x. So no, f and g are not inverses. Let's look down at the next example. We're going to do the same thing. We're going to start with f of g of x. So we're going to plug g into f. So you have 2 something squared minus 1. So that something squared is the square root. Remember, anything to the 1/2 power is the same as the square root of 0.5x plus 0.5 minus 1. So the square root and the square actually cancel each other. So that leaves 2. Remember, 0.5 is the same as 1/2. So 2 times 1/2 is 1. So you get 1x plus 1 minus 1. So positive and negative 1. So we get x. So we are happy because fog equals x. But we aren't done. We have to prove then that goth is also equal to f, or x, sorry. So once you get one, you have to prove the other, but if you get something that isn't x, you're just done. Okay, so goth, so we're gonna plug f into g. So we have 1/2, and then 2x squared minus 1 plus 1/2 to the 1/2 power. We're going to distribute our 1/2 in. So we get 1/2 times 2, which is x squared minus 1/2 plus 1/2 all to the 1/2 power. A positive 1/2 and a negative 1/2 will cancel. And then x squared to the 1/2 power. Well, we know a power to a power means you multiply. We also should know the square root of x is, or the square root of x squared is x. So we get x for both, so we are happy, and therefore they are inverses. So that kind of leaves us at a summary standpoint. So to summarize, basically our big ideas are if f of g of x equals g of f of x equals x, then they are inverses. Anything else means they are not. If you have a point is AB, then on F inverse, the point would be BA, because the domain and range of inverses flip. To find an inverse, you have to replace f of x with y, switch x and y, solve y, replace y with f inverse x. I think those are our big ideas. You have to know that the points switch, they are inverses, and then basically just that in order for a function to have an inverse, it must pass the horizontal line test. Just like in order to be a function, it has to pass the vertical line test. In order to have an inverse, it has to pass the horizontal line test. So a quadratic doesn't necessarily have an inverse unless you change its domain. Thanks, guys.